How that's done. Okay, inside the sun, you've got the sun burning bright. The up quark from the proton to make more mass. This goes back to Einstein's equation that everybody memorizes, but nobody knows what it's about. E equals mc squared. Okay, the energy, 15 million degrees. Right here. 15 million degree Kelvin. The core of the sun is able to fuse the protons to the point where the up quark receives enough energy to increase its mass. The up quark becoming a down quark. Draw it bigger. You will see these letters the same size in any chart in the world. Draw it bigger. The down is more massive than the up. The charge, electromagnetic charge on the up quark was plus 2/3. The charge on a down quark, minus 1/3. So, conservation of energy, conservation of matter, these go back to Newtonian physics. This is modern high energy particle physics. Conservation rules still follow. Electromagnetic, plus 2/3 to minus 1/3, there has to be a positive charge lost somewhere. A positive 1 is carried away by what's called an anti-electron. This is antimatter in the sun. This is not science fiction. I go to conferences all over the country. Graduate students, PhDs, think antimatter is something only on Star Trek. The sun creates antimatter. The first reaction that has happened. So, a positron, an electron with a positive charge, has to also be emitted. Now this is antimatter to offset the matter that was created with the down quark. So we've got a conservation of matter, we've got a conservation of electromagnetic charge. If there's time, I'll explain to you. Electricity and magnetism are the same thing. They just happen to have these direction vectors that are perpendicular to each other. But for simplistic purposes, conservation of charge, electric magnetic charge, conservation of mass. There's one more quantum quantity called spin. We spin like this, but it's an imaginary force that needs to be accounted for. This is where the particle, if you've heard of neutrinos, it's pretty much confirmed they have mass. These neutrinos are pretty fascinating things. They get the Greek letter mu, and from matter antimatter, because this is an anti-electron, this is actually a real neutrino. When radioactive decay happens, antineutrinos are emitted. The antineutrino was first discovered in South Carolina at the Savannah River Nuclear Power Plant. Some guys, Frederick Rains, and got the Nobel Prize for this. But a neutrino is emitted in the sun. It's so tiny, the mass is so tiny, there's supposedly, I've heard, as many as 1 trillion going through your eyeball right now from the sun. That's how dense they are. These are from the beginning reactions again. So the first reaction in the sun, if you can get this reaction, any element through plutonium up to the biggest now, which is probably verified anyway, 112 protons, 180 some neutrons, all started at this phase in stars. The sun is doing this right now to make helium. We have to be older than the sun. There's elements, carbon, iron in your blood, carrying your hemoglobin's oxygen and carbon dioxide around. That iron was created in stars before the Earth. could even be revolving around the sun, because the sun is still making the first step of neutrons.